How fast does a wave propagate down a piece of string? How can a rope wrapped around a pole keep an entire boat in place? How does the pressure of the Earth's atmosphere change as altitude changes? And how strong is the electric field around a large charged metal plate? These are all fairly simple sounding questions. You may have even learnt the answer to some of these at school. But as is the case with a lot of material that we learn, it tends to be just formulas handed down without any explanation of where they came from. Hopefully, by the end of this video, not only will you be able to answer these 4 questions, but you'll be equipped with a tool that can solve hundreds of other physics problems, a few of which I'll leave as food for thought at the end of this video. Suppose you have a light, uniform piece of string, pulled under tension. One end of the string is vibrating up and down, which causes a transverse wave to propagate down the string. If we want to know how fast the wave is, we first need to understand what the wave is. Let's focus on a single point on the string. We can see it's only oscillating up and down. In fact, any point on this string is only oscillating up and down. But what does this tell us about the forces acting on the string? Well, there can't be any resultant horizontal force acting at any point on the string. And importantly, this means that the speed that the wave propagates at horizontally is the same at any point on the string. Whilst this sounds obvious, I mean, of course the wave moves at the same speed everywhere on the string, but it means that we can focus on finding the wave speed at one conveniently chosen point, and we know that this must be the same everywhere else on the wave. Secondly, let's note that the vertical displacement of the string is a function of 2 variables: the position on the string and the time. If we try to solve this problem in a stationary frame of reference, as we are now, dealing with both of these variables is far from straightforward. So, how might we abstract the need for one of these variables? Imagine moving at the exact same constant velocity as the wave. In this frame of reference, the wave appears to be stationary. That is, we no longer need to worry about the time at all. The displacement of the wave is now only a function of position. Also note that every point on the wave now appears to move at the exact same speed horizontally, but in the opposite direction. And finally, because we aren't accelerating, the forces behave in the exact same way. I'd encourage you to just take a moment and make sure you fully understand this change in perspective. We're now ready to start solving this problem. It's difficult to consider the entire wave as a whole, so let's zoom in to one small length of string at the peak of a wave. Label this so-called infinitesimal length of string delta x or dx, which I'll use interchangeably throughout this video. We can label the 2 tension forces acting on each side of the string. The horizontal components cancel out, and the vertical components add together to give a resultant force of 2t sine theta. Using Newton's second law, F equals ma, we now have an expression for acceleration. But recall we said that each point on the string appears to move at a constant horizontal speed. Also, at the peak of the wave, the vertical velocity of the string is 0. Therefore, we have a horizontal velocity perpendicular to the direction of the resultant force. So, in our frame of reference, the infinitesimal length of string is performing circular motion at this exact moment. Again, just take a moment to let that sink in. We've gone from viewing the wave as a stationary observer to viewing it as a moving observer, and found that at the instant the string reaches the peak of a wave, the forces are just such that if this acceleration was constant, this small piece of string would move on a curved circular path at constant speed. But we can derive another expression for acceleration during circular motion. Consider a particle moving around a circle at 2 points separated by an infinitesimal time interval. Acceleration is rate of change of velocity, but because the angle delta theta is small, delta v equals v delta theta. Similarly, the displacement delta s equals r delta theta. After a bit of rearranging, we get that a equals v squared over r. Returning to our first expression for acceleration, we can equate these two. If mu is the mass per unit length of the string, then m equals mu delta x. Also, theta is a small angle, so delta x equals 2r theta. But that means we can cancel this from both sides, which leaves us with the well-known equation v squared equals t over mu. So the speed of the wave only depends on the material of the string and the tension in the string. Isn't that just wonderful? And we haven't even done any calculus. Well, just yet. Speaking of which, we can now move on to the next problem. Suppose you have a rope wrapped around a rough pole where the total angle the rope has been turned through is theta, and you pull at the rope from one end. What is the maximum force which could be applied to the other end of the rope before it slips on the pole? I'd encourage you to pause and try this yourself. Let's move to a bird's eye view. As you might have guessed, we're going to focus on an infinitesimal length of the rope. Unlike the first problem, the tension on each side of this section of rope won't be the same because we have two other forces: the friction between the rope and the pole, and the normal reaction force from the pole on the rope. Suppose the tension on each side of the rope is T and T plus delta T. Friction prevents the rope from slipping, so acts in this direction, tangent to the pole. Next, if we let the section of rope subtend an angle of delta theta, we can start resolving forces. The rope is stationary, so there is no resultant force on the rope. Vertically, we get the following expression, and horizontally we get this expression. The maximum frictional force occurs when F equals mu r. Also, since delta theta is a small angle, we can use the small angle approximations for sine and cosine. Note that the delta t delta theta term is effectively zero. That is, multiplying two infinitesimal quantities together gives something so small we can effectively treat it as zero. So once we substitute in for r in the second equation, everything nicely simplifies down to give delta t equals mu t delta theta. Finally, to find the total maximum tension on the other side of the rope, we want to sum up all of these little delta t's. Luckily for us, the integral is just the tool for that. The actual computation of the integral isn't important to this video. What's more important are the steps that we took to set up this integral in the first place. However, I'll show the details on screen now. After a bit of rearranging, we get that the maximum tension on the other side is exponentially larger than the inputted tension. And if there's one thing to know about exponentials, it's that they grow extremely quickly. Even just your body weight and 3 turns around a reasonably rough pole can withstand over 8 million newtons of force. Hopefully that explains why, if you have a spool of string, it almost always unravels before it slips. So far we've been dealing a lot with infinitesimal changes in angles, but what other infinitesimal changes could we consider? Well, modelling the Earth's atmosphere turns out to be a great use of them. Again, you should pause and try to think about how we can model the effects of altitude on pressure. Of course, when modelling something so complex, we need some assumptions. Firstly, we can assume that air is an ideal gas, so satisfies the equation PV equals nRT. We can also assume that within the troposphere, temperature decreases almost linearly with altitude. And finally, we can assume that gravitational field strength is approximately constant. Now, to find how pressure varies with altitude, we can consider a thin, infinitesimal slice of the atmosphere with thickness delta H. Assuming this slice is stationary on average, the upwards and downwards forces acting on it must be equal. If the slice has area A, the upwards force from the air pressure below is PA, and the downwards forces are the weight of the slice, as well as the downwards force from the air pressure above, P plus delta P times A. The volume of the slice is A delta H, so letting the density be ρ, we can rewrite the weight. Simplifying down gives delta P equals minus ρ g delta H. Density is just mass over volume, but we can link this to the ideal gas equation with a constant. Then N over V equals P over RT. So finally, we can use our linear model for temperature to get temperature as a function of altitude. Substituting in for ρ in our original equation, we're now ready to sum up all these little delta p's using an integral as we did before. Again, the details of the integral aren't too important to this video. But after a bit of rearranging, we arrive at the remarkably accurate barometric model for pressure in the atmosphere. And just for fun, if we plug in a few numbers, we can see why airplane cabins need to be pressurized. The ambient pressure is only about a quarter of what it would be at sea level. Also note that using a different constant of proportionality for temperature to altitude, the so-called temperature lapse rate, can let us model even higher layers in the atmosphere. The final problem I asked at the start of this video was about the electric field strength around an arbitrarily large metal plate, with charge density sigma at a distance h above the plate. It's not completely obvious what infinitesimal quantity we should consider, but before starting to answer this, I think it's a good idea just to establish some basics about electric fields. An electric field is just a region in space where a charged object will experience a force. A point charge will produce its own radial electric field. Intuitively, the strength of the electric field should be proportional to the charge, and should get weaker the further away from the point we are. In particular, if you imagine a spherical shell propagating outwards from the point charge, the flux is evenly spread over its surface area, so the field strength is inversely proportional to its surface area, 4 pi r squared. Combining these two results with a constant of proportionality, we get the most basic equation governing electric fields. The next thing to know is that similar to how forces add together to give a resultant force, multiple electric fields can superpose on top of each other. And this is exactly how we can deal with the charged plate. The most obvious infinitesimal to consider is a small rectangle of side lengths delta x and delta y. But before doing any computations, we can make one important observation. Any point on the plate has exactly one mirror image. Okay, but how exactly is that useful? Well, consider the electric fields produced by these 2 points which are mirror images of each other. Any components of the electric field parallel to the plate will cancel out. This means we only care about the components of the electric field perpendicular to the plate, and that makes our lives much easier. The charge of this infinitesimal area is sigma delta x delta y. And we can use a bit of Pythagoras to find the distance from this small area to the point a distance h from the plate. Plugging this into our formula from before, we get the infinitesimal contribution to the electric field. Finally, to find the component of the field perpendicular to the plane, we multiply by the cosine of this angle. Because cosine is adjacent over hypotenuse, we get left with this expression. All that's left to do now is integrate in both the x and the y directions. Since the plate is arbitrarily large, we integrate both bounds from -infinity to +infinity. Now, again, you're completely welcome to carry out this integral yourself, and I'll show the details in just a moment. But I want to take a step back to the point where we chose our infinitesimal quantity. The problem we're dealing with is highly symmetric. I'd encourage you to pause and try and see where I'm going with this. Note that we have radial symmetry, as every point on a circle like this is equidistant from the centre. Perhaps this suggests considering concentric rings of thickness delta r on the metal plate. Since delta r is small, the area of each of these rings is approximately the same as if we unravelled it to a rectangle of width 2 pi r, the circumference, and height delta r. Hence, the charge on this ring is sigma 2 pi r delta r. Again, we can use Pythagoras and cosine to find the vertical component of the electric field at every point on this ring. Finally, when we come to integrate this time, r varies from 0 to infinity, and now we only have a single integral to deal with. Well, as promised, now's the time where we actually compute these integrals. After a bit of reverse chain rule, inverse trigonometry, and limits, when all's said and done, both approaches, thankfully, give the same answer for the electric field strength, which is sigma over 2 epsilon naught. But do you notice something interesting? The h cancelled off. Our final answer is completely independent of the distance from the metal plate. What we've just discovered is the uniform field. Of course, in practice we can't have an infinitely large metal plate, but as long as the length of the metal plate is much larger than the distance h from the plate, this result will hold. And furthermore, we can do some fun things with this. You may recognise if we have two metal plates of opposite charge, the electric fields will constructively interfere between the two metal plates, giving E equals sigma over epsilon naught, and will destructively interfere outside the two metal plates, giving E equals 0. Not only can we create a region in space with a uniform electric field, but we've effectively built ourselves a parallel plate capacitor. It's always much more satisfying to understand why something is true than to just be told that it's true. Now that the video is coming to an end, as I promised, I'd like to leave you with a few more questions, which you're free to have a think about. I've left some of these deliberately vague, and I'd encourage you to leave a comment if you have anything you'd like to say about any of these, or perhaps if you have an interesting problem of your own using infinitesimals. With that being said, I hope that you've not only met a real-world application of all the calculus that you might learn in school, but you now also understand why infinitesimal objects are so essential to all of physics.